welcome back to ECE 501B. Today what I want to remind you of is your homework is due on Friday, and I think that's at 11:59 p.m. and there's a Dropbox available if you want to take that length of time to do it. Don't count on getting into the ECE building at that point of the day. If you're handing it in to the physical mailbox, which I do have, you can do it, but make sure you do it by 6 p.m. or sometime like that on Friday. Maybe the building is open for a little bit later. If you have access to the building, then you can submit it until 11:59. And obviously I won't know if it's in at 12:02 or 11:59. I will know if you do it via the Dropbox. And homework 2 will be assigned, and it's due a week beyond homework 1 is the plan. Today what I want to do is, I'm assuming you've already watched or seen 3 lectures. You had, if you're in class, you've seen 2. There's a third that is available for you. I knew you would be wanting to do something over Labor Day, so that was available for you to watch, and that completed our material in Chapter 1. We are now starting Chapter 2 with finite dimensional vector spaces. Chapter 1 was really dealing with these vector space concepts and the definitions. Now we are going to talk about what happens when we deal with just a finite list or a finite set of vectors. That allows us to begin finite dimensional vector spaces, and today we'll talk about span. That's an N and not an M, not spam. This is span, and that means basically where can you get to from these vectors? What do they span? Linear independence of vectors and dimension. Those are some topics that we will cover to get us thinking about where we are. We can go to the left path, which is our finite dimensional direction, and talk about linear algebra. Or later in the semester, a lot of these concepts will have an analogy with infinite dimensional ideas, and that's in the second book, Frank's, which is functional analysis. And we'll hopefully be able to, and you can hopefully make that connection when we get there, but now concentrate on finite dimensional ideas so that you can make that transition more smoothly. That's the idea. Today then we're talking about Chapter 2, which is finite dimensional vector spaces in the yellow book or in Axler. And the first concept that we want to discuss is span. And that means that if you're given a list of vectors, what's buried in that list of vectors? Phrasing. You could maybe think of a matrix, but I'm thinking now concentrate on the word list. What does list mean? Pardon? Order, well, that was, yes, so order matters. And another piece of that is it's finite dimensional. The list has a finite number of entries. So given a list, a finite number of vectors, let's just say that we'll call those v sub 1, v sub 2, v sub n. And let's say those vectors, that list of vectors is drawn or extracted from or taken from a vector space. Since we're using little v's, let's call our vector space capital V. The span of the list of just those n vectors, v sub 1, little v sub 1, little v sub 2 through little v sub n, that's the span of the list is the set of all possible linear combinations of the vectors in the list. And that may seem somewhat wordy, but let's see if we can make sense of that. And we will actually write that using the following notation. We will say the span of v sub 1, v sub 2, v sub n, some list of vectors, n of those, that's actually defined to be this collection of a1 v1 plus a sub 2 v sub 2. Here is our linear combination of vectors plus a sub n v sub n, such that, that's what that colon means, all of these a sub 1s, a sub 2s, these scalars that we're scaling the vectors with, those belong to our field of numbers, be that real or complex. And we'll go through some examples in a little bit. But that's the way that we will define span. If somebody says, oh, I have two vectors, v1 and v2, and they say, what's the span of those vectors? Then the span is wherever you can get to, whatever you can touch, by linearly combining those vectors with arbitrary scalars from your field of numbers. Let's look at an example so that you have something concrete to think about. And to provide it something that I can sketch a little more easily, let's simply look at a plane or two-dimensional space. Suppose our vector space V is R2. And let's say that somebody gives us the following vectors, V1, 3, 3, and I might write those as a row, I might write those as a column. But here I have two components, 3, 3, in a vector V1, and let's say V sub 2 is a vector 4, 5. Somebody might ask, what is the span of V1, V2? Does it span the entire vector space, capital V, or does it span some subset or subspace, hopefully is what we're talking about, is there a subspace that those vectors span in the original or the underlying vector space, capital V? The thinking that you might be wanting to do is probably very visual or graphic. You might say, well, what if I simply looked at those vectors in the two-dimensional plane? And I could think of the first coordinate as being x and the second coordinate being y. The first one, v sub 1, is 3, 3, which now says that I go over 3 and up 3, and this would be v sub 1. V sub 2 is then 4 in the x and 5 in the y, and there's v sub 2. And you want to know, what do those vectors span, v1 and v2? And hopefully it's clear that those are not on top of each other. They're close, but we're not so worried about close. We just want to make sure they're different from one another now in the general setting. And numerically, this might give you numerical issues if they're close but not on top of each other. They may be numerically too close to be giving you good numerical information. But here we're not concerned with this. We're concerned with this in the theoretical sense. And since v1 and v2 as vectors are not on top of each other, these actually span the entire plane R2. You can get to any location in this two-dimensional plane by a linear combination of V1 and V2. That's really what you're saying. If V1 and V2 span all of R2. Here's a way of verifying that, or let's say producing a solution to what is the span of V1 and V2. We can say we have the span of V1 comma V2. That's equal to A1 V1 plus A sub 2 V sub 2, such that A1 and A2 are coming from the field of real numbers. Or putting a little bit more information in there, or explicitly identifying what V1 and V2 look like, we're scaling V1, which was 3 comma 3, with an A sub 1. We're scaling V sub 2, which was 4, 5, with A sub 2, and we can scale those with any A1 and A2 coming from the real number field. Or we can now identify the x component, or the x coordinate, and the y coordinate in this A1 and A2 parameterization, or parameterized form, and we now have 3A1 plus 4A sub 2 giving us the first coordinate. We have 3A sub 1 plus 5A sub 2 producing the second coordinate for any A1, A2 in our real number field. And now we can basically say, if somebody gives me a first coordinate z sub 1, an arbitrary z1, and they give me an arbitrary z sub 2, can I pick A1 and A2 to provide that? That's really what we're saying. And we could then say, just let z1 equal 3A1 plus 4A sub 2, and z sub 2 is equal to 3A1 plus 5A sub 2. And since those right-hand sides are not the same, we know that we can, and A1 and A2 are different, we know that we can get arbitrary Z1 and Z2. And we can actually produce that arithmetically, or with some linear algebra, essentially. We can say, oh, here's Z1 and here's Z2. If somebody gives me a Z1 and Z2, can you tell me what A1 and A2 are? That's another way of sort of looking at that. And we can do that by simply rewriting this and say Z1 as a matrix, or I'm sorry, Z1 and Z2 as a column vector are parameterized by A1 and A2 in the following way: 3A1 plus 4A2 and 3A1 plus 5A2. Or if we pull out the matrix that scales the coefficients A1 and A2, we have 3A1 and 4A2, and we have 3A1 and 5A2. And we can find A1 and A2 since these columns or rows are not the same. We know those are, well, I'm getting ahead of myself, but we know that that matrix can be inverted because those columns are linearly independent, which we'll learn in a minute. But if we now just do the matrix inverse of that matrix, now somebody can actually explicitly give us the coordinates Z1 and Z2. We can pre-multiply by the inverse of 3, 4, 3, 5 and produce these coefficients A sub 1 and A sub 2. And you all remember the nice little way of finding the inverse of a 2 by 2 matrix? That one doesn't carry over into higher dimensions, unfortunately, But we can just say 1 over the determinant. And now we do what to what's left in our inverse matrix, or in the matrix that's inverse? We simply switch the locations of the diagonal entries, and we negate the off-diagonal entries. And that's now the inverse of that original matrix. And you could follow the definition if you wanted to on a matrix inverse. This is 15 minus 12 in the denominator, or 3. And we have our 5 minus 4 minus 3, 3. Or we could say, let's go ahead and push that scalar all the way through, and we now have 5 thirds z1 minus 4 thirds z2 minus z1 plus z2 is how we would combine these desired coordinates, let's say z1 and z2, to produce a1 and a2. That's how we could do it mathematically, by turning the crank and simply saying, oh, I have a matrix problem, let me just invert the matrix. Or we could do it by 2 equations, 2 unknowns, and step through that process. We could say, I don't like messing with matrices maybe, but I know z1 is equal to 3a1 plus 4a sub 2. Z sub 2 is equal to 3a1 plus 5a sub 2. I can now subtract those, and the first coordinate, a sub 1, is eliminated, and I now have 4 minus 5 a sub 2, or minus a sub 2, and now I have a form for a sub 2, which is c sub 2 minus z sub 1, and in fact that's what we had in the last row of our matrix solution, or in our first solution. We can now use that value for a sub 2 in the first equation or the second equation. If we now plug that result into the top equation, we have 3a1 plus 4a2 is z2 minus z1. We take the z's to the other side, and we have 5z1 minus 4z2 is equal to 3a1, which now allows us to solve for a1 by dividing both sides by 3. And we have now 5z1 minus 4z2 over 3, and that's what we had before. Meaning for any choice of z1 and z2 in R, which is what we need for these vectors to span all of R2, then the span of v1, v2 is z1, z2 in R2 for any arbitrary values z1 and z2 elements in our field of real numbers R. And that's actually equal to V, which is actually equal to the two-dimensional plane. Meaning if somebody now gives you z of 1, 0, where this is now the first coordinate z1 and this is the second coordinate z sub 2, Now we simply plug those Z1s and Z2s into our formulas for the A2 and the A1. If Z2 is 0 and Z1 is 1, A1 is simply 5/3, and A sub 2 is -1. Or we can now rewrite Z as 5/3 times V1, which was 3, 3, minus, or plus A sub 2, 4, 5. With the appropriate V1 and V2. That hopefully gets us on the same page when we start talking about span. Now let's talk in general terms. If here's a proposition, and proposition you could sort of think of as a theorem. I think last time when somebody asked about proposition, I was thinking postulate. A postulate is usually just a fixed fact, and you accept that, and then you derive everything from the postulates. But these are propositions, so we should be able to prove these. We won't prove many of these, but here is a proposition. The span of any list, and again, that list is some finite collection of vectors in V is a subspace of V. So you give me any list of vectors in V, the span of that list will be a subspace in V. And it doesn't have to be, I mean, what are some of the subspaces of V if V is R3? R3 would be a subspace. The entire vector space would be a subspace. What's the other extreme? 0. We have to have, so a non-empty subspace would be the additive identity. So if we say we have a non-empty subspace, a subspace has to have 0 as one of its elements. That would be the smallest subspace of a vector space, would be the additive identity, the 0 element. So if we say we have a non-empty subspace, we know we at least have to have the 0 element in that subspace. We could have a line in R3. We could have a plane in R3. Those are, we could describe as a list of vectors, and their span would form a subspace of V. And I said we weren't going to prove all of these. Let's prove this one. So here is a proposition. It says the span of any list of vectors in V is a subspace of V. If somebody starts talking about a subspace, what's the first thing that needs to start going off in your head? How do you show something as a subspace? Or what is needed to show a subset? So if I give you vectors from a vector space, they're at least a subset of that vector space. How do you show that that subset of V is a subspace? You remember what we talked about when we said, how do you verify that a subspace or a subset is a subspace? Okay, so it has to have those three facts. It inherits quite a bit because of it being a subset, and all we have to really verify are three different pieces. Has to have the additive identity, needs to have, were you going to answer or ask a question? Okay, so I'm going to answer first, because I think I heard the answer here, and then I'll listen to the next question. But it has to have the additive identity, it has to be closed under addition, and closed under scalar multiplication. Question. So the closed under addition, does that imply that it has the additive identity? Or did you... Good question. The question was, can it be closed under addition and not include the additive identity? That's what you're asking, right? So yes, so what I think we need to think about, though, is the minimal case. So something could be closed under addition. How do I want to say this? If we had one vector, and it was, let's say, 0, 1, and that was your only vector, that would be closed under addition. And let's say that we can't, well, yeah, if we take the -1. I was thinking if we just restricted our field to be the positive numbers, then it would just always be going in the positive x direction. And we wouldn't be... So if it's just one element, then we just keep going sort of in that one direction. And so the minimalist subspace that we need is the additive identity. So to have a non-empty subspace, we need the additive identity, or the 0 element. Now if we go bigger than that, now we need this closed under addition, or we can have this additional property of closed under addition. So we could have well, I'm not sure that that's the best answer, but I'll think about it and see. But we're going to accept the fact that we need to show three things. We need to have a 0 or a non-empty subset. We have to have it closed under addition and closed under scalar multiplication. All right. So now let's suppose U is a subset. Then we need the three properties that we just talked about. We need to have 0 belonging to U. That's our additive identity. We need closed under addition. And closed under scalar multiplication. Now, we want to talk about the span of any list of vectors in V being a subspace of V. And we now know that if we have a subset or a list of vectors that might form U, capital U, we want to show that that collection, that list, satisfies these three properties. That's what we want to do for any collection or any choice of a list in our original vector space, let's say up here, which we were calling capital V. Let's say we're given a list. Of vectors. Let's call that list W. And inside that list, our vectors are now going up to Michigan. V sub 1, V sub 2 up to V sub m, not V sub n. Just changing notation a little bit. And here, that's in little v, or I'm sorry, in capital V. We want to know, does the span of that list form a subspace? The span of W is defined by, or is equal to, all linear combinations of the vectors V sub I in W. Okay, that's by definition of the span. Now, all elements in the span are elements in V since V is closed under addition and scalar multiplication. Or we could say the operations used in forming linear combinations. Are addition and scalar multiplication. Which really says that the span of W is a subset of V. Because we can take all elements in the span are elements of V, and so they're forming a subset of V. And that actually allows us to sort of say that the span of W is a non-empty set, but we can also show that sort of here. Let's say that we now have 0 is equal to 0v1 plus 0v2 plus up to 0 v sub m, and that's a linear combination of our list of vectors. So that belongs to V. But all of our scalars are 0, and so the resulting vector is 0, and that gives us our additive identity in V, and that's a part of, or that's a linear combination, or comes from this list forming W. So that this says that 0 now is an element of the span of W. And that's one of the things we wanted to show. We need it to have that property, and now we've shown that the 0 or the additive identity does exist and it belongs to the span of W. We simply weight all of the vectors with coefficients or scalars of 0. And that gives us this 0 vector. Now let's take W1 and W2 as elements in the span of W. What does that mean? That means that W1 is some linear combination of the V's, and we had M of those V's. And we'll just pick some coefficients with some subscripts. Since I'm now subscripting the vector W1, let me sort of double subscript my coefficients or scalars. I now have a sub 1, 1 V1 plus a sub 1, 2 V2 on up to a sub 1 M V sub M. That's how I will build W1. So I'm going to take W1, and that's in the span of W. I'm going to take W sub 2, and build it up in a similar fashion. And now I want to know, is W1 plus W2 in the span of W? Is it closed under addition? And W1 and W2 are generic vectors in the span of W. Which allows me now, in this parameterized form for W1 and W2, I can now say, oh, I now have A11 plus A21 times V1, A12 plus A22 times V sub 2, and on down to A1M plus A sub 2M V sub N. Now, all of those coefficients, the A11 plus A21, the A1M plus A2M, all of those coefficients are elements of whatever field of numbers we picked them from or started with. And that's because F was a field, and we have the field is closed under addition, and we're now adding those elements of that field, A11 plus A21, for example. So all of these coefficients are elements of F, since F is a field which is closed under addition. Which allows us to conclude then that W1 plus W2 is in the span of W if we pick W1 and W2 from the span of W. Now we need to do, is it closed under scalar multiplication? So now let's take an arbitrary vector in the span of W. Let's say take W1 that belongs to the span of W, and let's take a scalar from our field of numbers, F. W1 is this, let's say A1 V1 plus A sub 2 V2 plus A sub M V sub M. If we now look at BW1, that's just B A1 V1 plus B A sub 2 V2 plus B A sub M V sub M. But each of those coefficients BA sub j's are elements of the field of numbers. Since our field F is closed under scalar multiplication. And because of that, or thus, we're left with a linear combination of the v sub i's that we started with. And that's in the span of W. So the span of W is closed under scalar multiplication, which now says, therefore, the span of W, whatever that set of vectors ends up being, forms a subspace or is a subspace of the original vector space V that we pulled those vectors from, that we created that span. What are some notes? So now you give me any list of vectors from a vector space, and that will form a subspace. Some notes. The span of a list of vectors is the smallest subspace that contains these vectors. So if you give me a list of vectors, the span of that list is the smallest subspace that contains those vectors. And there is a relationship to the concept of subspace sums, which was that additional lecture that you need to sort of watch on your own. If W is the list of all vectors, and let's say subspaces U sub 1 and U sub 2, then the span, of W is actually U1 plus U sub 2 as subspaces are concerned. However, we will see, let's say, maybe I should say soon see, this spanning set, that's the W, is able to be reduced in terms of the number of vectors. Meaning somebody could give me 1,000,000 vectors in R2, and maybe that spanning set is not going to give me any more information than 2 vectors in R2. And so I can maybe reduce that collection of vectors down to a well-defined number of vectors that span the same set or the same space. Terminology. If somebody says if the span of V1, V2 up to V sub n is V, all of V, it equals the vector space V, then the vectors V1, V2 up to V sub n are said to span V. So if somebody says these vectors span V, that simply means that they are covering or completing or completely representing the vector space V. Let's now talk about finite dimension. A vector space V is said to be finite dimensional if it is possible to construct a finite length list of elements that span V. If somebody gives you a vector space V, and you can now find a finite list of vectors that spans V, then that vector space is finite dimensional. Once we have this notion of finite dimensional and span, we need to start maybe talking about how easy it is to create these lists, and are some collection of vectors maybe more informative than others. And that's then this topic of linear independence. Oops. the vectors in a list let's say v1, v2 up to v sub n are said to be linearly independent if the only linear combination of the vectors that equals the zero vector is the one, meaning the one linear combination where all of the coefficients are zero. Meaning, if we have a1 v1 plus a sub 2 v sub 2 plus dot 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 plus a sub n v sub n, if that equals the zero vector, then v1 and v2 up to v sub n are linearly independent if and only if that equation is true for a1 equal to a sub 2 all the way up to a sub n being 0. Then these vectors v1 through v sub n are linearly independent. If the only way that you can get 0 is if all of those scalar coefficients are 0 themselves. We can actually state that another way. This is equivalent to saying none of the vectors in the list can be written as a linear combination of the remaining vectors. If we have a list that's linearly independent, then we can't linearly combine those vectors to form one of the vectors in that list. If we can, then that list of vectors is no longer linearly independent. Here's a corollary. If a list of vectors is linearly independent, then none of these vectors can be written in terms of the other vectors. So we've just written that comment or that note as a corollary. Let's see if we can prove that. And here what we want to do is use the proof technique called the contrapositive. So let's now proof by contrapositive, which means that we need to show not B implies not A. So in our corollary, what is A? A is a statement. And what is statement A in this corollary? We have a list of vectors that's linearly independent. That's statement A. What's statement B? Statement B says none of these vectors can be combined to create any of the other vectors. That's statement B. So the first thing that we want to do is negate statement B. Statement B says we can't write any vectors in terms of the others. Well, let's do the opposite, or let's negate that. So let's actually assume that we can write a vector in that list in terms of the other vectors, or some of the other vectors. That's going to be our first course of action, creating not B. Suppose let's say the list of vectors are labeled such that we have the following. Suppose we have V sub n is equal to A1 V1 plus A sub 2 V sub 2 plus A sub n minus 1 V sub n minus 1. And we need one of those scalar multipliers to be non-zero. If we didn't have that, then we wouldn't be negating B. We need to get some vector in our list. We're going to label that as the V sub n vector in this list of n vectors as a linear combination of the other vectors, which says that we have to have at least one of those coefficients to be non-zero in order to be a linear combination of the other vectors. So we need with at least one A sub I not equal to 0. Is that okay? Now we have just defined these labelings of the vectors. We're assuming we have n vectors, and we're saying take the nth vector, V sub n, and write that as a linear combination of the other n minus 1 vectors. And we're saying that's now a true statement. And that's actually not B, isn't it? So we're assuming not B. Now that we have this, we need to demonstrate that that implies not A, and you told me A was the list is linearly independent. And if a list is linearly independent, what do we know about that list and linear combinations of that list relative to the zero vector? All the coefficients have to be zero, don't they? So now we're looking to try to show that we can create the zero vector out of a non-zero combination of vectors. One way to get the zero vector is to just take a vector and subtract it from itself. That gives us the zero vector. And the vector that we will use is v sub n. Let's now, in our next step, say that we now have v sub n minus v sub n. That, I hope you feel comfortable saying that's 0. But what is that? In terms of what we've listed up above, that's now a1 v1 plus a sub 2 v sub 2 plus a sub n minus 1 v sub n minus 1 minus v sub n. And now what are we saying? If we look at the right-hand side, that says that we have a1 v1 plus a sub 2 v sub 2 plus a sub n minus 1 v sub n minus 1 minus v sub n, but that's equal to 0. Now, in order to be linearly independent, we would need all of those coefficients, those scalar coefficients, they'd have to be 0 in order to get the zero vector. But we know that one of these, a1, a2, these variable scalars up to a sub n minus 1, one of those is non-zero. And we also know that this coefficient, this minus 1, is non-zero. So we now know that we have two non-zero scalar coefficients that produce a zero vector. And that means that those vectors are not linearly independent. And that's not A. So we've now shown that this combination of the original vectors is equal to 0 with at least two coefficients being non-zero. That then means that the list of vectors is actually linearly dependent. A contradiction, which is what we were setting out to show. That now says that we ended up with not A. So we started with not B, so maybe that a contradiction is maybe not the best thing to say, but we showed that not B implies not A. And that then is taken together, that's the proof by contrapositive. Here's a question. Can a list containing the additive identity be linearly independent? Can a list containing the additive identity be linearly independent? So now you give me a list and you include in that list the additive identity. Is that list linearly independent? Yes. No. So I have an answer. I have one no. Do I have any more no's? 2, 3. I feel like I'm at an auction. 4. Do I have any other bids? Any? So, so now what you're being asked is, can you find a list containing the additive identity, which, when you combine any vectors in your list with scalars from your field, can you have any of those scalars non-zero and still come up with the zero vector? If you can, then your list would not be linearly independent. The only way that this list of vectors can be linearly independent is if that forces all of your scalars to be equal to 0 to get the 0 vector. Is that making any sense? It seems like I'm being very wordy. Let's see if I can justify that with writing down some vectors and scalars. The answer no is correct. That's the correct answer. And here's a way of justifying or answering the why or the why not. Suppose I now have a scalar, a sub 1 times v1, plus a sub 2, v sub 2, plus, let's say, a sub n, v sub n, and that's equal to 0. Actually, and let me say that I've labeled my vectors such that that last one is the additive identity, the 0 vector. So here are my vectors, and I'm creating a linear combination of those vectors, and I'm saying here's a linear combination of those vectors that produces the 0 vector. If these vectors, v1 through v sub n, are linearly independent, all of these coefficients need to be 0. But this coefficient, I can take that to be anything I want, can't I? It doesn't have to be 0 since it's scaling a 0 vector. Maybe all the other a's are 0, but now I have just one scalar that's not 0, and that's violating my condition. I can now pick this particular scalar. I can take any value without affecting the sum. And so that now tells me that if you have the additive identity, that can't be in your list of linearly independent vectors. So you can't sort of throw that one in and introduce any new information into your list of vectors. That doesn't belong. So we're in Sesame Street mode. One of these things is not like the others. One of these things just doesn't belong. That 0 vector doesn't belong in your list, right? Because it will not maintain linear independence. Now, to get you something to chew on over the next few days, since we won't meet until next Monday, let's just quickly look at what is called the linear dependence lemma, which means we're not too far into Axler, but maybe it takes a little bit of time to get through each page of Axler. So 25 pages of Axler may be a little bit longer read than 25 pages of a novel. Don't get discouraged if it takes you a fair length of time to read one page of the book. But this is on page 25 of the textbook. This is now saying given a linearly dependent list, A, it is possible to find an element of the list that is expressible as a linear combination of the remaining elements. I.e., or that is, that element, it's in the span of the other elements. So given a list that's linearly dependent, then you can find an element in that list that can be formed from a linear combination of the other elements in that list. And that proof is similar to what we've done above. But now if somebody starts talking about vectors that are linearly dependent, now you know you can go into that list and pick one and say, oh, I can express this as a linear combination of the others. Now you may have to go in and find several vectors to linearly combine to create that element. But so so the question was, this sounds like you have to use all the other ones. I can say that you can. The scalars might be 0. So you now can find a linear combination of the other vectors or elements of that list that will add up to that element in the list, one of the elements in the list. And we'll pick up at that place on Monday.